the technical director at TECMO. I have been working in the industrial sector in Lebanon, the MENA region, and Africa. I have had the opportunity to work on a wide range of projects, helping to solve problems and improve efficiency. I have learned a lot from these experiences, and I am here to share some of that knowledge with you today. I also have the pleasure of teaching system simulation and system thinking at UZEC. System thinking has given me a unique perspective on how to approach complex problems. One of the key things I have learned is the importance of seeing the big picture and understanding how everything is interconnected. This is especially true and very helpful when it comes to energy conservation. My father, an engineer who graduated from ESTP, Paris in 1922, instilled in me the importance of not wasting energy. He firmly believed that even small actions like turning off a light could make a difference. I remember once when I was a kid, I left the light on in my bedroom. He reminded me that we shouldn't waste energy, even if we can afford to pay for it. This lesson has stuck with me, and it's why I'm so passionate about this topic. In my experience, both as a consultant and in general, I have noticed that people often take energy consumption for granted. They see the electricity bill for their factory or the cost of air conditioning as just another expense, something they are used to paying. What they don't always realize is that these costs can be questioned. There are often opportunities to make significant savings, sometimes as much as 30 or even 50. Some of you may have heard me talk about getting more out of diesel generators last year here. Today, I want to broaden that discussion and make it relevant to everyone, not just engineers. We'll talk about ways to recover energy from generators, but as well as other energy-saving measures. And I share examples from my own experience, so you can see how these ideas work in the real world. I'm proud husband, father, and grandfather to two energetic grandkids. They constantly remind me why energy conservation is so important for their future. We should shift our focus from energy economics and finding ways to save money to spend elsewhere to energy ethics. Wasting energy should be considered morally wrong, even if we can afford to pay for it. Mr. Reed, he said, energetic crime. So let's dive in and explore how we can all save energy, save our planet, and make a difference. Simple calculation number one. If you consider we have between in the industrial field, okay, my presentation mean. So if we have a 100 kilowatt machine working either 7 days, 24 hours, which happens sometimes in some industries, or 5 days, 24, or 5 days, 8. Per year we have this much hours. It will consume 875 kilowatt. If we consider the USD per kilowatt is 0.25 cents, the bill will be 220,000, 150,000, or 75,000. if you want to make things for 1 kilowatt, so each kilowatt will cost $1,500 in an industrial environment. Calculation number 2, they are very easy, straightforward. So a 100 kVA generator will probably consume around 1 kilogram per hour of diesel. If it runs for 50,000 hours, this means it will consume about 9 million kilograms of diesel, 9,000 tons, let's say at 850, 765, 7,650 USD. So now consider the impact of efficiency. If this generator is, if we choose one which is 1% more efficient, we will save $76,000 in its lifetime. 1%. So the cost of a generator like this most probably is around 150,000. So, and if you are going to choose between two, one is at 150, the other one is 180. If the one which is 180 is 1% more efficient, and sometimes it could be 3, 4, 4% or even 6 or 7% more efficient. I will not follow my notes. Simple calculation number 3, very simple. I worked for a dairy factory. I had to choose between two machines. One was for 50,000 and the other 100,000. So this machine will advocate 20,000 liters per day, 20 tons, for 300 days a year, 15 years. The processed liter is 19 million liters. And the cost of milk was still probably 0.75. It will process $67 million cost of, let's say, raw materials. The additional cost of 50,000 represent $0.0005 per liter, which is something like 50 Lebanese pound. But we are spending 50 Lebanese pound per liter, but we are gaining in the production stability. We are probably the efficiency. We are gaining 5,000 or 10,000 lira per liter. So this is to give you an idea. When it comes to industry, the stake is very high in general. HVAC systems, all these first are obvious. We will not talk about them. But I will speak about temperature set points. Adjusting thermostat set points can have a big impact on energy use. In cooling mode, each degree increase in cooling increase will save 5 to 8%, especially when we are in a mild climate like Lebanon. And zoning divides a building into different areas with separate temperature controls. This allows for customization based on occupancy and use. This is the first slide. Spot cooling. Many factories face the challenge of excessive heat from machinery, making it difficult for employees to work comfortably and productively. Air conditioning an entire factory is often too costly, but spot cooling offers a smart alternative. By focusing cooling efforts on specific areas where employees spend most of the time, we can significantly improve their comfort and well-being. We utilize high efficient fan coil that use high temperature water like instead of using water at 5 degrees, we are using water at 15 degrees because we want that the breeze that is coming on the people to be around 25, 27, not like normal air conditioning where you get the outer temperature at probably 17. This prevents overcooling, which can lead to health issues like cold or stiffness. Our experience showed that spot cooling can dramatically cut energy costs compared to cooling an entire facility. It's a win-win situation for both company, bottom line, and employee satisfaction. Yesterday, we had a real success story in spot cooling in a large plant for the great satisfaction of the employees. Textile duct. Textile ducts offer a revolutionary solution, especially for the food industry. Not only they incredibly easy to clean, preventing the build-up of harmful contaminants, but the textile itself can act as a filter. This means we can use a low-pressure fan, saving you a significant amount of energy cost. We can further enhance this by using large refilters before the textile duct to remove large particles before they even reach the duct. And for the food industry, the white fabric makes it easy to spot dirts. This is a project that we did in Kampala. The project involved a massive factory, 150 meter by 150 meter, covering a total area of 22,000 meters square. To meet extensive ventilation requirements, we used textile ducts. Our design incorporated large textile ducts of 1.5 meter diameter. This approach proved to be highly effective, providing efficient air distribution. Here for the fan that we have used, we use this highly efficient fan with adjustable pitch for optimum performance. We had recent supply challenges due to the drone industry demand for these fans. So now we have difficulties to get them in Lebanon because they may think that we are using them for drones. But because they are very efficient. We operate here at 30,000 and and 150 Pascal, consuming 3 kilowatt, almost 3 kilowatt, and we use 20 of them. The total was 60 kilowatt for this factory. The competitor, they have suggested this kind of fans with a small filter and a duct that you can never clean. And I looked at the electric motor, and I've seen that it is 15 kilowatt, and most probably this duct is not for 30,000, it's probably maximum for 15. And imagine if they have used this kind of system, instead of 60, they would have consumed 300 kilowatt to make be ventilation for this area. And 300 kilowatt, if you go back to simple calculation, 3 times that per year, at least they are working 594, ends up $450,000 per year, and the project cost was something like 250. So payback in less than 1 year. But to achieve the lowest possible air pressure drop in our system, we took a comprehensive approach. In-house calculation and simulation focused on louvers and the rain shield. The problem was to get a rain shield that will not oblige us to go more than 150 Pascal. Okay. Next, also I'm always talk about refrigeration in the industrial sector. So this is, all we know that a refrigeration system consists of compressor, condenser, and evaporator. But if we look at this graph of compressors, and there is something that we call COP, coefficient of performance. If you have a coefficient of performance of 10, let's say, that's me for each kilowatt that I put in my machine, I will get 10 kilowatts of cooling. And working, let's say, at an evaporation in a normal chiller, I work at an evaporation of 0, and in the worst case scenario, let's say at 50, this one, okay? And 0, I have a coefficient of performance of 2.8. But if I need water for my plant to cool down my molds, and I need this water at 15, in this case I can make with an evaporation of 10, and if I increase the capacity of my condenser to condense instead of 450 to go down even with 25 or 30 using a cooling tower, so the 30 is here, and 10, I'm now at 8. So 3 times less electric consumption by choosing the current chiller for an industry. And these chillers, most probably they consume like 200 kilowatt. Instead of consuming 200, they are consuming 600. Okay? But we have to watch out when we, if it is an air conditioning in my house, I use it probably 100 hours per year. It's not the case when I'm an investor. This is a project that we have done also following the idea in the previous slide, that we have four circuits, but in fact 2 circuits. One that delivers at 5 degrees for the machine that needs 5, and one that delivers water at 15, 17 for the mold that they don't need less than that. And you imagine what is the economy, instead of having one chiller system, even if it is a chiller with ammonia that has a good COP in general, but it will not be 3 times or 4 times the COP of any other system. Here I put this photo in it's not industrial here, but it's in university, in an engineering university. They have the condenser in front of another wall, so the air will circulate like this, and if you take the temperature here, most probably is 60 degrees. So you see on the previous paragraph how much we are losing. 60 degrees, the efficiency, the COP can go down to 1.5. Here for aesthetic, they have put louver, and here too. So the air will blow, and on the other side you have the suction, so it will, the same air will blow, and if you measure the temperature here, you can get sometimes like 50, and your condensation will be 60 or 65. Here also we have the condenser, one facing each other. So this, the hot air will be sucked by the second air conditioner. Here they have put the things in a technically very well, but in fact they destroyed the unfortunately كمان هيك thermal energy storage also in the industrial sector. Thermal energy storage, specifically ice banks like one shown here, offers solution for managing energy demand with both industrial and commercial. The concept is simple. We store energy during the night, in fact, here, when the electricity, the tariff is low, and the outside conditions are good for condensing the refrigerant, so you can have higher COP, and they also allow, in general, in the industry to shape the peak load. Refrigeration system and photovoltaic. When preparing this, I thought that the advantage of having a thermal storage with the photovoltaic, combining the solar with the photovoltaic, has a big advantage. That in this case, during the day, we can store the energy in the ice banks by getting the energy from the solar panel. And you can increase the amount of solar panels that we have. And the advantage also is that if there is a passing by cloud, we can stop the generator instantly. You cannot do this with a machine in the industry. You cannot, if there is a cloud passing by that is affecting our PV. So I have seen that in general they keep running one or two generators for this purpose. But combining with ice banks, and we can stop the compressor instantly. Put some detectors around to be able to detect. Probably if we detect half a second before, it's more than enough to stop a compressor. If hydraulic circuits, before when I was preparing, I thought it was pump, but then thinking about holistic, it's better to speak about hydraulic circuits. Hydraulic circuits, if we see the pump curves, a pump curve works best in this region, which is 76% efficiency. But when we run the pump in this region, we go down to 55, and here to 45. And seldom I have seen pumps working in this region because they select the pump the technician will select the pump. He is happy to have a pump with high head or whatever, and they don't know that they are in fact consuming 50% more energy because the efficiency is dropping from 75, 76 to 45. And a 10 kilowatt, you can say 1 kilowatt, a 1 kilowatt is 5,000 hour a year, 5,000 kilowatt hour, this is $1,500, which is the price probably of the pump. I have to go, so this is understanding system requirements, like I said before, having the whole picture, right size of pump, match the pump to the application, regular maintenance tasks also. I will skip these. If you want to get the PowerPoint, I can send it to you, no problem, with some also the Excel sheet that we will see next. Compressed air, I will skip it because we don't have insulation. Only I want here to pinpoint that with insulation, if we have a bare pipe at, and the water, let's say, is at 80, a bare pipe, the surface temperature will be around 80, and the heat loss is 263 watt per meter. Imagine how much we are losing sometimes per meter, 260 watt of heat. If we put a 15 millimeter insulation, it drops to 55. Most probably, it's, if we go to 40 millimeter, it drops from 263 to 25. Probably a little bit acceptable. For a 450 process temperature, we can lose something like 5.6 kilowatt if it is not insulated. So this is to pinpoint how much the insulation is important, especially when it runs for 6,000 hours a year. Energy recovery system from diesel exhaust and jacket water benefits. It's energy saving, it's less pollution, it's higher generator efficiency, and minimized fuel consumption. Usage, hot water, steam generation, drying, space heating, other industrial process heating, preheating, and finally absorption cooling, because in many places they don't need the heat that we can provide from the heat recovery. We can, with absorption machine, give them cooling. This is how we make the calculation. I will not go through it. The one who are interested, I can send you. You can on my LinkedIn. I will send you the file. It is a 6,000 kilowatt plant working at 40%. 2,400 kilowatt per hour. Generator cost is around 2 million. The whole setup, work running time 24 hours. So we go through this calculation, and we go through. We know how much there is gas flow, 19,000 kilogram, 19 ton per hour, and at what temperature, and we know what temperature we need. We need a steam at 160 degrees, 6 bar. So we consider that the flow exit is 200. So we will recover the heat from 410 to 200. And we have put here that there is the system efficiency 70%. And even if we can get this amount of heat, but we put also a usage factor of 75%. It depends, sometimes it's 100%, but because most of the time, even if they have this capacity, it's too much for them. But in other, especially in industry, they are ready to use the 100%. Hot water, this is the amount of hot water that we can get from the radiator, and we consider the 75 and so on. We had made all these calculations, and the payback, the system cost was something around 1 million, and the payback was 0.71. This is, I've made this for 10 years project, and I use the IRR, internal rate of return. I changed the kilowatt cost. If I increase it now, it gives me an IRR, positive IRR, that I'm making money. If I decrease it, it will be negative. So when it is zero, in fact, this is my cost. In this case, I'm integrating all these, even with the price of the machine or whatever, I end up knowing exactly my cost this way. And we did the same with the heat recovery, and we end up that with the heat recovery, the cost here is 0.207, and without the heat recovery, 0.287. So we decreased in other way the cost of the kilowatt from 287 to 207. This is the cost distribution. The fuel cost is 81% of the total, and the generator cost was miscellaneous oil maintenance. This is true for large systems, industrial systems. One thing also that we took, in fact, in Pepsi, they have this 315 Caterpillar 2000 kVA, and the belt, they have to change the belt twice a year. This is a budget for 5,000. The bearing replacement once every 2 years, 25,000. So they have to pay each year $1,700. But the fan consumption on the generator is 59. And we put in, because we are cooling now the generators not by the radiator, but we are cooling it by, we are getting this heat in the recovery. We should consider that we are saving 59 kilowatts, but we put 15 kilowatt as a heat dissipator, because we are using also sometimes when they don't use fully our the heat, so we have a backup dissipator. So we are in fact saving 44 kilowatt hour, and for 6,250 hours, this makes $150,000 saving only from the radiator fan. And it seems it's why the manufacturer is not using a remote radiator like the one we are using with 15, because these generators, in fact, they are meant to be compact, and they have a small radiator with a very powerful fan, and they are also either be compact or installed on a tractor or whatever. So they are or to be used as backup. If we are using them as a backup generator, it will run for 100 hours a year maximum. So, but in our case in Lebanon, we are running this for almost all the time. saving is huge. The generator, how do we do it? The generator, you have the fumes, it goes into the heat exchanger, and this is where we recover the heat. If we are not recovering the heat fully, we are obliged to put here a diverter. In case here we are not recovering the heat, the diverters will open to the outside. This is the diverter has a double hinge to be very tight. This is my, I do this for instead of playing cards. So, this is how it works, and it is really very efficient because it has 2 hinges. Sometimes, instead of putting here the diverter, in one case, one client, he didn't want to have any pressure on the generators when our heat exchanger is working. So we did for them this setup. We put a high temperature fan that it will sucks the heat through the heat exchanger, and we have 3 temperatures here. We try to keep this temperature a little bit lower than this one. That means that we have some of the air from outside going in, and the generator will sense the pressure, the normal pressure, the atmospheric pressure, because it is always open to the outside. This is the setup that we do for jacket water. Also here, if we don't want to, you have installed these on brand new generators under guarantees, all these projects, some projects, that the easiest way to not interfere in the setup of the generator, here we have the water coming out to the radiator, we pick it out and we re-inject by this pump. So we take the heat, and if in case we are not cooling enough this water is going back to the radiator of the generator. So nobody can argue that we, at one time, we didn't cool sufficiently the radiator, because even if it will pass by this, it will go to the generator. The drawback is that we can, with this setup, have something like maximum 65% recovery of the heat, because also the heat that is coming out here is still hot, and we are there is a heat rejection to the outside here. Another one, which is a little bit more complicated one, but in fact, instead of re-injecting at this stage, when we are when the system is on, we re-inject after the heat. And in this case, we can go up to 85% efficiency in recovering the heat. This setup also is, we had water 72, it's heated to 82, and then with the exhaust to 90 or even more. It is pressurized water, you can go to 200 degrees C. This is a system, we have done one with 99, the output, and here the input was 20 degrees from the well, with a 15 kilowatt generator, 1600 kVA generator. We provided 150 meter cube per day, that they were heated from 20 to 99, 150 meter cube per day. This is the system that has for the radiator heat recovery. The advantage here that we have these are the generators, here are the users, and in case the users are not really cooling properly to the water, the jacket water, we have installed here two four that we call dissipator. This is air dissipator or water dissipator to keep the generators properly cooled. And we have installed on a brand new generator this system, and in fact we took the whole responsibility that we are cooling properly the generator jacket cooler. This is a system at PepsiCo. You can see here is also this is one of the biggest that we have done at Sweden. It can give up to 4.5 tons of steam per hour. In general, our heat exchangers are very large too, because here in Lebanon we are using oil and a lot of good quality, so we have to have large diameter pipes and very easy to clean, so we end up with a huge machine, but the payback is less than 1 year. Also, we have made here the treatment for the flu. Here we have a wet cyclone to be more effective than a normal cyclone. This is also at UNDP. We have made pressurized water at 200 degrees. Others. This is the last one we have done. It's spot under. This is a complete system where we have the generators and we have chillers and we have heat pumps included, that they also they work on the heat coming from the generator. Quickly. And few slides here only to stress about the importance of system thinking approach in when it comes to energy economy. In fact, I said before, not energy economy. Now we should not speak about energy economy no more. In fact, so understand energy conservation as a dynamic, interconnected system, because the heat that is being produced somewhere can be the waste heat can be used elsewhere. So we have to have always the big picture, leveraging employee knowledge and motivation. In systems thinking, we have to keep all involved in the project. It's not coming like I'm the technical guy, I know about energy recovery, energy economy, and I will, you have to follow my instructions. So we have to include, because for a lasting impact, education, provide ongoing training on energy saving practices, empowerment, encourage employees to identify and report waste, action, implement employee suggestions. Not only they have to report, but they will be more happy when they see that their suggestions are being implemented. The motivation of continuous monitoring, real-time energy data displayed on the screen. This is extremely important, because they should have like a screen where you know the ratio. Let's say how much we have saved per kilowatt of produce or per kilogram of or per ton produced. So this continuing monitoring help people to react more quickly. Incentives, reward individual team energy saving achievement, recognition, celebrate successes to inform, real-time feedback, transparent data, policies and feedback, increased agency, faster result, energy audits and benchmarking, conduct regular energy audits to identify potential areas of improvement. This is we can by energy audits, and it's good also in the spirit of system thinking that the audit should be from the company outside, because and the control should be a third party. Comparison between PV and diesel engine heat recovery. I want to say this is the SNAKE that you know, the SNAKE project on number. This is a wonderful project. I was amazed, and I'm advocate of this project. But once I made this calculation also, that heat recovery at CDM was in the same period. We the steam hourly production was 4 tons. In fact, it's more. We consider it as 4 tons. It was 4.5 at max, but normally at 4. Energy economized 2 million kilogram per hour. Diesel economized 220 kilogram per hour. Yearly economy 1,900 tons. CO2 emission that we have cut is 600 tons. Project cost was around 1 million. So the ratio of 167 USD per ton of CO2 had paid, let's say 167 USD to save 1 ton of CO2. These figures I took them from the ministry website. Yearly electricity production, this much tons economized, CO2 emission cut, project cost 4 million. We had to pay 3,400 USD to economize 1 ton of CO2. The ratio between the two is 20.4. And I have put 70% on the heat recovery of CDM that probably they will not use totally the heat. It is 14.3. 40.3 times less, let's say, what we, and this is green. Thank you. مين حدا عنده أسئلة؟
الفانز اللي استعملتهم
لا مش هيدي، هي غلط، هيدي فانز فوق، هيدول الباقي، بس هي الفانز هي اللي فرجيتها تاني واحدة هوريزونتال مع دب، بس كله مدروس لحتى ما يكون في أقل بريشر دروب، يعني دب بتلاقيه شيء إنه نفق. Otherwise, we can no more use these kind of fans. زي بتروح على
عفوا في الاكسل استعملت الفلو اكزوست وعلى اساس عم تتكون بس هي عندها طرق سيفتي.
ايه يعني هلا ثابتكم ماشي، نحن عم ناخذها قديش هو عم يمشي فيها تطلع وتنزل بس ان افريج هي. يس. You have to neutralize it.
نفس الشيء حتى اللي حاطه مش عم بتمرق الاكزوست بايب بكونوا مثلا عن سلكشن عم بكونوا ستينلس ستيل تبعك
هي كله ستينلس ستيل. هيدي لقلك يعني هو ما كثير بيأثر على المي. ما كثير بأثر على النقص، بأثر أكثر على الصوت.
بس بالجروب تبع جاكيت كولي كان في محل عم نرجع للدور قبل ما نفوت شو اسمه بالتاني روب.
خلص شيلوا لي بركة.
بسألك إياها.
Okay, thank you Mr. Bshara. راح نكون مع آخر سيشن اليوم مع Mr. Martin from Hazer. Martin, can you hear us?
Yes.